Okay, chapter 16.2, we're going to be talking about vector fields and line integrals. So these are kind of two different ideas, but they're going to relate together. So vector fields, this is kind of a new concept that we're going to introduce and talk about first. And then we're going to look at how they relate to line integrals. And that's what we talked about in chapter 16.1. So it's going to be kind of an extension of line integrals, not just over functions, but now through something called vector fields. So let's begin by talking about what vector fields are. So vector fields made up of two different words, vector and fields. We know what vectors are. We've been working with those this entire class. And now the word fields, that kind of implies that there's going to be some collection of these vectors across a space or across a region. So it'll be a field of vectors. Just as a little notation note, there are two different ways to write a vector field. A vector field can be written as a bold capital F, right? So it could look like big bold F, right? Or the way I will typically write them is you can also write them as a capital F with a vector hat on top. So both of these will indicate that the function you're looking at is a vector field. To begin, let's just take a look at an example of a vector field. Right, so here is something you might be familiar with. This is a wind, speed, and direction map. So if you can imagine that at every given point in this field, right, we have a vector attached to every point that has a direction and a magnitude representing the velocity of the wind, the speed of the wind, and the direction it's going at every point in space across the oceans. So you can imagine that if you were a ship sailing through the Atlantic, you could kind of like drop in your boat here and you would see that the vector field would push you kind of in this direction, and then you might come up here to Africa and kind of get pushed to the west into the Caribbean. And so you could see that the forces in the vector field would push you along a path that looked like that. As a convention as well, the way we write or the way we draw vector fields is that we attach the tail to each vector, so the bottom, to the point that it was evaluated at. So the velocity at this point corresponds to this vector, right? So we attach the tail to the point that it's representing. Right? So that's just a little convention as well. And so a vector field can be written generally like this. So a vector field F, so big F with a hat on top, would be represented as some function, right? Maybe we'll call it F, with an amount in the I direction, plus some function in the J direction, and some function H in the K direction. Right, so it is the output of this function here, right, is a vector with an I and a J and a K component, and then these functions F, G, and H tell you how the point in space relates to it. So here is a note about what vector fields is. So vector fields, they are a function. They're a function whose output is a vector, right, with direction and magnitude, is a vector evaluated at each point in the region. Right, and so depending on how many components your vector field has, in this case it's 3, it can be a 3D vector field, or it could be a 2D if you only had 2 components. You could have a one-dimensional vector field, so it can be of any dimension. Right, of any dimension. Right, in our example vector field, this would be a 2-dimensional vector field. And so we would have, like, take this point, and maybe in our coordinate system we call this point like 20, 56. Maybe that's the point it corresponds to. We could plug in the point 2056 into our vector field equation, And the output for this specific vector field would be a vector with this magnitude in that direction. So it might look something like negative 1i plus 0j or plus 0k or something like that. So that would be an example of a real vector field. So let's take example 1, and this is just an exercise in sketching vector fields and seeing what they look like. So let's try number 1 here. So I'll get 1, 2 axes. So here's our y and our x. So let's start at the origin. So we're going to start at the point 0, 0, and let's plug that into our vector field equation. So 0i plus 0j, that's the 0 vector. So there's no vector that lives at the origin. Let's try the point 1, 0. Let me draw it out a little bit farther. So here's 1, 0. So that would be 1i plus 0j. So that's 1 unit in the I direction and 0j. We can try the point 2, 0. So that would be something that looks like this. So here's 2, 0. That would be, again, 2 in the I direction, 0 in the j. So that's the same one, same direction, but twice the magnitude. Let's try the point 1, 1. So here's, let me try that better. So here's 1, 1. So that would be 1i plus 1j. So that's something that looks like that. We can try the point, how about we try 1, 2? So let's try this point up here. So here's 1, 2. That would be 1 in the I and 2 in the j. So that's actually something that looks like that. And we can try on the y-axis as well. So the point 1 or 0, 1 would give us 0i plus 1j. So something that looks like that. Oops, went away. So here's that vector. And then similarly, this one is going to be twice the length. So if you can see a pattern, all of these vectors are going to be pointing directly away from the origin with a length that kind of corresponds to how far away it is. So if we were to sketch a couple more just to get a representative picture of what this vector field looks like, they would look something like this. Right? So all pointing away from the origin with a magnitude that's kind of related to how far away it is. Right? Oops. All right, so this is what that vector field would look like. Right? And these points will be a little bit longer. Okay, so that's a sketch of that vector field. Let's try this vector field. So number 2, let's put down some axes again. And we'll start with the origin point again. So 0, 0 also gives us the 0 vector in this case. The point, how about 1, 0? So in this case, 1, 0 would be negative, so 1, 0, so 0y. So that's 0 in the I direction plus 1 in the j direction. So now it's kind of flip-flopped a little bit. So we have a 1 vector, so we have 1j. Let's try the point 2, 0. So in this case, we have 0i plus 2j. So now this one's twice the length. And now we can try 3, 0. So 3, 0 would be the similar idea, 3 times the length. Right, so something like that. We can try the point 0, 1. So now it's going to be negative 1 in the I direction plus 0j. So that looks something like that. And this is a similar idea that as you get away from the origin, they're just going to get longer proportional to that component. So it'll look something like that. We can try the point negative 1, 0. So that will give us 0i minus 1j. So that's negative 1 in the j direction. And you might be able to start to identify the pattern. Most vector fields will have some pattern to them that you can start to see after you sketch some points. And then, without even evaluating, you can kind of tell that these are going to go something like this. So this vector field kind of would represent, like if you imagined that these vectors in this vector field represented the velocity of water in a river, this might represent what a whirlpool would look like. So this equation might be the vector field for a whirlpool in a river where the center of the whirlpool is the origin. Right? So you could imagine that if you were to drop in a leaf into this vector field, it might spin around. It would be a little bit faster the farther away you are, and then as you kind of rotate in, you would get slower because those vectors are of smaller magnitude. So here's two vector field examples that we looked at. Now there's a third specific vector field that we've already seen before that I just want to identify as actually being a vector field. Right? We didn't have the name vector field yet to give it to you, but we remember finding the gradients of functions back in chapter 14. The gradient of f of any given function is a specific type of vector field, and this is going to be super important in the coming chapters, so I wanted to point it out relatively early. So if you remember, the gradient of f was written as this, like the upside down delta of f is equal to the partial of f with respect to x in the I direction, right? So we have some function, where was it? Yeah, so some function in the I direction. Just in this case, the gradient gives you the specific function to put in front of each component, right? Plus the y partial derivative in the j direction and the z partial derivative in the k direction, right? So the gradient is a vector field. So this will be important in the next chapter. So let me make a note of that. So this will be important later. It's important now too, but it will also be important later. I'll put an exclamation point there and a star. So the reason we're introducing vector fields is because we can do line integrals through them. Right? So in 16.1, we talked about line integrals of functions, where you would integrate a function along a curved path C. Now, if this is, for example, your vector field, you can have a curved path C. Maybe that's your curve. Maybe it represents the path that a boat took through the Atlantic Ocean. The interpretation of a line integral through a vector field is how much of the vector field is acting in the direction of travel, right? So in the direction of your curve. So you can imagine here that kind of at the beginning, you would be accumulating a lot, like the integral would be adding up quite a bit, because it looks like these vectors are mostly in the direction of the curve here, right? Even more so here. That's very in the direction. So you would be accumulating a lot of the vector field. Now here the vector field seems almost perpendicular to your path of travel. And because a line integral through a vector field, it tells you how much of the vector field is in the direction of travel, this would actually give you almost zero accumulation here, because the vector field is acting orthogonal to the path of integration. So the way we would write that is a line integral through a vector field. So this is line integrals through vector fields. The way we'd write that is the integral over some path C that's traversing the field. You're integrating the vector function. Dotted dr. So this dr is the differential of the curve, right? Because we write our curve C is written as like r of t. And so this right here is a differential in the path of integration. And the reason we're dotting the path of integration, where we're doing the dot product of the path of integration with the vector field, is because the dot product tells you how much is going in the same direction. It's that projection of f onto r. So the more parallel they are, the bigger the dot product is. So the dot product here would almost be at its maximum, right? Whereas the dot product here is 0, because the dot product of two orthogonal vectors is 0. Right? So that is what we're solving. But this is not a super usable form because it's in terms of a dr differential, which we don't usually use. The usable version of this is the integral from a to b of our vector field, right, written in terms of the path, which is what we did in chapter 16.1 as well, times the first derivative of r dt. We can write, so all we're doing here is we're rewriting the vector function in terms of the path we wrote times its first derivative dt. So this almost looks identical to 16.1. The only difference is we're not taking the magnitude in this case. And instead of having just a general function f, we have a specific vector function capital F, where where r of t is the path of integration. Path of integration, and you have to bound t, right, your parameter between a and b, and those become the bounds of your integral. So let's actually try applying this to an example. So let's start with example 2. So example 2 is asking us to evaluate the line integral of a vector field, and I know it's a vector field because this is big capital F, right? So I know we're doing a vector field equation dotted with dr, which is that vector field line integral formula, the integral of f dot dr, where our vector field xyz, so this is a three-dimensional vector field, is zi plus xyj plus y squared k along the curve c given by r of t equals t squared I plus tj plus the square root of tk, and then we have the bounds of t, the parameter here. So everything's kind of been given to us. We just have to assemble it all. The first thing I want to do is I want to rewrite the vector field. So we'll rewrite big F in terms of t, our parameter that we're integrating with, in terms of t, using r. That's what this is saying right here. So rewrite f in terms of t using the vector field equation, or using the curve equation, excuse me. So let's do that here. So f in this case now becomes, let me rewrite it this way. So f of r of t, so in this case zi, so we plug in the z component of our curve. So that'll be the square root of t, let me get my marker, square root of t in the, I direction, plus x times y in the j, which is going to be t squared times t, so that's t cubed in the j direction, plus negative y squared, so that'll be minus t squared in the k direction. So we rewrote the vector field in terms of our path of integration. Now we need to find dr dt, so the first derivative of r. So let's find dr dt. So dr dt, in this case, will be 2t I plus j, right, 1j, plus 1 over 2 root t k. Okay, so I believe that's the first derivative. Now we just plug it all into our line integral through a vector field formula. So this will become, let me pick a different color. That's the integral from 0 to 1 of this, right, this dotted with this. So I'm going to do it all in one go. So we're doing component by component multiplication. So the I times the I plus the j times the j plus the k times the k. So the sum of the components multiply. So in this case, that will become 2 times t to the 3 halves. So 2t to the 3 halves plus t cubed plus 1 half, I'm trying to do this in my head, t to the 3 halves. All of that dt. All right, so I combined this step of doing the dot product into one step. So I have the entire integrand solved for. So now, this is all just power rule stuff. So this will be pretty easy to evaluate. So let's do that real quick. I'll evaluate over here. So that's going to be, let me get the inside. So the integral of 2t to the 3 halves. Actually, let me combine these together. So I'll combine this t to the 3 halves with 1/2 t to the 3 halves, which will give me 3 halves t to the 3 halves. So I'll add these together. And the integral of 3 halves t to the 3 halves will be 3 halves times, right, 2/5 t to the 5 halves. Plus, and then the integral of, what do we do next? Plus the integral of t cubed, which is 1/4 t to the 4th. All that evaluated from 0 to 1, which will give us 17/20. So there you go. That is the answer to how much this vector field acts along this curve when you integrate from 0 to 1. Right? So that's 0 to 1 is that segment of C, and this is how much the vector field is acting into the direction. So how much of it is parallel across the curve. One of the big applications of line integrals through vector fields is finding work. So work is an interpretation of a vector field, of a line integral through a vector field, if something is true. So if the vector field you're integrating, so if F is a force field, or so what that means is that the output of each of those vectors is in units of force. Or so maybe it's a gravity field where all the arrows represent the force of gravity at any given point. Or maybe in this plot right here, maybe these vectors represent the force of water at any given point in the river. Right? So if F is a force field where each vector represents force, then when you integrate through it, you're finding how much of the force is acting in your direction of motion. Then the interpretation of this is work. Because you're adding up how much of your direction of motion is in the direction of force. And if you remember, in work, you only accumulate work if you're moving in the direction that the force is pushing, right? So we're finding how much of the force is pushing in the direction of motion. Right? So that's a really nice interpretation. So most of the times we're going to be solving these line integrals through vector field problems, it'll usually be in the context of finding work where that vector field is a force equation. So let's try number 27. So number 27 is asking you to find the work, right? So we already know we're going to be doing a line integral through a vector field done by this force. So it is a force written as a vector field, right? So that's our vector field equation. And here it is. Over the straight line from 1, 1 to 2, 3. So we actually weren't given a curve C. We have to construct our own path of integration, giving that information. So we're going to construct, I'm going to construct R first, given that. And so I know that I can write the parametric line equation from the point 1, 1 to the point 2, 3, and that'll be our curve of integration, which in this case, the curve is just a straight line. So let's do that real quick. So I know to get my v, the direction vector from those two, I'll just subtract 1, 1 from 2, 3. which gives me the vector, so 2 minus 1 is 1, 3 minus 2, or 3 minus 1 is 2. And then I'll pick my initial point to just be the initial one. So that'll be 1, 1. So then I can write the parametric version of this line as the point plus the vector component times t. Right, so 1 plus 1t, and y will be 1 plus 2t. Right, so here's the parametric form of the line that gets us from 1, 1 to 2, 3. And now let's just write it in terms of r of t. So r of t then becomes the x part, which is 1 plus 1t. So that's 1 plus t in the I direction, plus 1 plus 2t in the j direction. Right, so this is now our path of integration. So we parameterized the straight line segment from 1, 1 to 2, 3. All we have to do now is bound t between two things, so we just get that segment of the line. And in this case, if you plug in 0 for t, you get the 0.11. And if you plug in 1 for t, you get the 0.23. So this is a really nice way to write that parametric equation. Now, let's write the vector field in terms of the equation we just wrote. So in this case, f of r of t will become, so x times y, so we have to do so we have to basically FOIL these, so x times y will become 1 plus 3t plus 2t squared. Yep. In the I direction. And then it's y minus x. So it's the difference between y and x in the j direction. Let me move this down real quick. I keep selecting parts of other things. Well, that should be less than or equal to. So it's plus, so the difference between, so 1 minus 1, and then 2t minus t just becomes t in the j direction. So there's our function written in terms of the parameter t. Now we can also find dr dt, because we have to multiply by that. So in this case, the first derivative of r is just going to be 1i, so it's just I plus 2j. And now to set up our integral, we just need to dot dr dt, right? We dot dr dt with f of r of t. So we're going to have the integral from our bounds were 0 to 1. Our function here is going to be this 1 plus 3t plus 2t squared times 1. Right, so that's going to be 1 plus 3t plus 2t squared plus 2 times t, which is 2t. dt. So this is a pretty easy integral. I'll just rewrite, I'll combine the 3t and the 2t to give us 5t. So I'll just put 5t here and then move everything in. There we go. I won't do the total evaluation for this either, but the answer you're looking for is 25/6. So when you integrate, when you move along this path in this force, right? So this is the force that's acting on you as you move along this path. It takes 25/6 amount of work to navigate that path through this specific force field. Okay, sweet. Example number 5. Let's try this one. So find the work done by another force field. So we're going to be finding work through a force in moving an object. Right, so you're moving an object along this curve. See? Parameterized by, so it's already been given to you. So we already have the curve in terms of t, plus a little bit more, and the bounds are given to you. So everything's kind of set up. Now we just need to find all the components. So let's start by writing, I always just start by rewriting the force field, so the vector field, oops, why is it not writing? In terms of t. So we get x in the I direction, which is going to be cosine of pi t I plus y in the j, which is just t squared j, plus z in the k, which is sine of pi t in the k direction. Okay, cool. So we rewrote our vector field in terms of t. Now we'll compute dr dt to get the first derivative. So what was our function? So the derivative of this is going to be negative pi, right? Because we have the chain rule, negative pi sine of pi t plus 2t. Oh, don't forget my vectors, plus 2tj plus cosine, oh wait, it'll be pi cosine of pi t k, right? Because we have that chain rule because of the pi on the inside. Now we'll do the dot product. I'll do this one separate just so you can see it all fully written out. So we're going to do the dot product of this, right, dotted with dr dt, because that gives us our full integrand. So in this case, we're going to do component by component multiplication. So we'll multiply I component with I component plus j component times j component plus k times k. So let's do that. So we'll have fully written out cosine, let me pull out the factor out front. So we'll have negative pi sine of pi t times cosine of pi t plus 2t cubed plus pi sine pi t times cosine of pi t, right? And then this, if you simplify it, that cancels out with that, right? So they cancel out. And so you're just left with 2t cubed, which means our final integral for evaluating the work is just going to be the integral from, or the bound 0 to 1, of 2t cubed dt, which comes out to be 1/2. Oops. So all of that simplifies to 1/2. So the interpretation of number 5 would be the amount of work it takes to move a particle through this path, right? Through this path from 0 to 1. So that's the segment of this path that you're traversing through this this force field. So through this force is equal to 1/2. So that's the amount of work it would take.